Okay, so now today we will be looking at the wind actions. We in the last weeks, week 1 to 3, we were discussing how to find the dead loads and live load on the buildings, and we used the standard 1170.1 to find the dead load and live load. In this week, we will be discussing how to find the wind loads on the building, and we will go through the wind actions first and some definition and some explanation of the wind action, and then we will go through how to find the wind load on the building. So let's start our lecture. So these images show some of the wind actions that affect the structures. So as you can see, the wind can cause some damage and debris that flying everywhere due to the damage made by the wind. And as you can see here, the wind also affects the trees and can make damage for the walls or the masonry walls like here. Also can affect the bridges, okay, and can also make some cyclones like this image here on the top. So the wind actions are severe winds that we need to consider in our design of the buildings. So I will show a video with some of the damage that can be done with the wind. Thank you, Ismat. I will upload the slides just after the lecture. Sorry, I was late to upload them. So you will have the access after the lecture. Can you see the video now? Can you see the video screen? I will start the video. So this was an example, guys, of how the wind can damage buildings. I hope you have seen the video and can hear the voice. So the wind is sometimes extreme and can damage the buildings like that. So we need to make sure that we consider the wind in our design or in our construction. This is another building or another video of buildings collapsed or failure due to the wind. You can have a look on this video as well. And now in some winds, due to wind, we sometimes have cyclones. So the cyclones are very extreme wind events that we need to consider because in Australia, some of the areas are subjected to cyclones or cyclonic events. So the cyclonic or tropical events are like giant engines that use warm, moist air as foil. So the cyclones happen in the tropical areas and it work like giant engines that use warm and moist as foil. That's why they form only on over warm ocean water and near the equator. So because Australia has some areas near the equator, that's why the cyclones are likely to happen in Australia. And this video here will show us an example of the cyclone. So I will open this video for you as well.
There are three basic stages in the life of a tropical cyclone: its origin or source, the mature stage, and the dissipation stage where it dies out. These occur in a continuous process, not as separate and distinct stages. Each stage may occur more than once during the life cycle as the strength of the cyclone rises and falls. It may reach land, weaken, then go back out to sea where it strengthens once more. The formation of a cyclone depends upon the following conditions coinciding. A large, still and warm ocean area with a surface temperature that exceeds 26.5 degrees Celsius over an extended period. This allows a body of warm air to develop above the ocean's surface. Low-altitude winds are also needed to form a tropical cyclone. As air warms over the ocean, it expands, becomes lighter, and rises. Other local winds blow in to replace the air that has risen, then this air is also warmed and rises. The rising air contains huge amounts of moisture evaporated from the ocean's surface. As it rises, it cools, condensing to form huge clouds about 10 kilometers up in the troposphere. More warm air rushes in and rises, drawn by the draft above. The rising drafts of air carry moisture high into the atmosphere, so that these clouds eventually become very thick and heavy. Condensation then releases the latent heat energy stored in the water vapor, providing the cyclone with more power. This creates a self-sustaining heat cycle. Drawn further upwards by the new release of energy, the clouds can grow to 12 to 15 kilometers high. The force created by the Earth's rotation on a tilted axis, the Coriolis effect, causes rising currents of air to spiral around the center of the tropical cyclone. It is at this stage that the cyclone matures and the eye of the storm is created. As the air rises and cools, some of this dense air descends to form the clear, still eye as the cyclone rages around it. The eye wall, where the wind is strongest, behaves like a whirling cylinder. Cyclones rotate clockwise in the southern hemisphere, anti-clockwise in the northern. The lowest air pressure in a tropical cyclone is always found at the center and is typically 950 millibars or less. The average air pressure at the Earth's surface is about 1010 millibars. Tropical cyclones have significantly lower air pressure than the air that surrounds them. The bigger the pressure difference, the stronger the wind force. One of the lowest air pressures ever recorded was 877 millibars for Typhoon Ida, which hit the Philippines in 1958, where winds reached 300 kilometers an hour. Once formed, the cyclone's movement or track follows a pathway away from its source, driven by global wind circulation. As warm ocean waters feed it heat and moisture, the cyclone continues to enlarge.
Thank you. So this was a brief explanation of the cyclone. Because the cyclone also happened in Australia, we need to consider the cyclone in our design. So one of the example, this was Cyclone Tracy, which occurs on the Christmas Eve of 1974 in Darwin, Australia, which caused a lot of failure and collapse of the material and also loss of this, loss of lives. So I will show you this example as well. Not fully, but just part of it.
Cyclone is imminent. Batten down your house. Remain calm and stay inside.
lost my flat, I lost my house, I lost my property, I lost everything I got. But when you believe my name,
Okay, guys, so this is just showing you example of the like the catastrophic events that can be caused by the cyclones. So this cyclone happened in Australia in 1974, and as you can see how it damaged most of the houses and most of the buildings in the city. So in some places in Australia, the cyclone need to be considered because some areas are cyclonic areas, which mean it is more susceptible to cyclones. Okay, so this was an introduction about wind and cyclone, and this also another video showing you how the wind and air pressure are related and how the wind is produced. You can watch this video as well. And then now let's start our lecture about the wind action and how it affects the building and how to consider in design. So the wind actions are forces that caused by pressures induced by wind passing over the structure. So the wind actions are the pressure or forces caused by the flow lines or the wind flowing around the building. So this wind will affect the walls and roof of the building. So as you can see in the top one side of the building will be under pressure, or the wind will push the wall from this side, the left side, and the rear side of the building, rear side of the building, or the rearward wall will be under dragging force or suction. So the wind has different effect on the sides of the building based on the how where the wind blow and the wall facing the wind. So, for example, to the bottom diagram or the bottom sketch, we have air moving towards the surface. So we have one surface, the red wall, is under pressure. So this wall facing the wind will be under pressure. And this wall is called windward wall. On the other side of the building, the wind will be dragging the wall or making suction on the building. This wall at the rear is called leeward wall. So suction and pressure can happen on the wall. Suction means the wall or the air moving away from the surface. So as you can see here, the wall is pulled by the wind. On the other side, the pressure side, the side is called windward wall, and the wall is pushed by the wind. On the roof mainly will be under suction, so the wind trying to pull out the roof from the house. So this is an introduction or the summary of how the wind will affect the walls and the roof. Okay, this is another example to us here. The pressure on the red wall. This wall is our windward wall. This windward wall will be under pressure. Okay, and as you can see how the wind is surrounding the building, so it will affect all the building sides facing the wind or side walls or roof. And here is an example of damage happened due to windward. So the wall facing the wind was damaged by the wind or the pressure from the wind. This is another part of the building affected by wind, which is the roof. So due to the wind flowing above the building and from the sides, so this wind will try to pull out the roof from the building. So the roof of the building will be under suction. So suction means the wind is getting or moving away from the surface, so it is pulling the surface. And here is, as you can see, we have example of a roof was taken out due to wind or wasn't moved away due to wind. And here also is a scenario of how the roof was coming out into air or moved away from the building due to the suction on the roof. So now we have pressure on the windward. suction on the roof. Another part of the building is the side walls. Side walls are the walls that not facing the wind or not in the opposite direction. So they are the side walls when the wind coming from this direction here. So this yellow walls are the side walls. The side walls also are subjected to suction due to the wind. So as you can see here in this example, this failure of the building, so the wind was flowing around the building, and due to the suction, it take out the side wall away from the building. So this for side wall, and this is a wind damage scenario for a side wall building, a wall of the side wall of a building. So this is the normal building before the wind blow, and the wind blowing from the side like that. So the wind start to pull out the wall, and when the wind become more intense or the speed of the wind increase, so the wind start to apply more forces until it takes out the side wall. Okay, so the wind also will affect or cause suction effect on the side walls of the building. The last part or the last wall type we have is the leeward. Leeward is the wall opposite to the wall facing the wind. So here, this wall is the windward. So the other one of the opposite direction will be the leeward. The leeward wall will be under suction as well. So mostly all the building will be under suction due to wind, except for the windward. And here is another example of how the wind damages the rear wall and the whole building due to this wind event. And here is another example of how the black or the leeward wall was damaged, and also the side walls was damaged. So to summarize this, we have four types or four actions on the building. The first one is the windward. So the windward will be under pressure. So the red wall here is the windward under pressure. The next is the roof. The roof will be under suction. The side walls will be under suction. And finally, the leeward under suction. So 3 are under suction, 1 under pressure. These are the wind actions we will consider in our course, but there are some other wind effects. So as you can see here, other wind effects, internal pressure. So all the wind we discussed earlier was on the external surface of the building, but also the internal surfaces of the building are subjected to wind when you open the door, for example, or when you open the window. So if the door open or the window open, the wind will cause internal pressure on the internal surfaces. Another type of force is the drag force on long roof or long side walls. For example, this very long building. So when the wind blow will cause like horizontal force, try to drag the building in the horizontal direction. So there will be like force try to drag the building in this direction. Okay, so this force will try to drag the building. Another is the drag on the individual members of the building, like the electricity or the power tower here. So the drag force can be on parts or members of the building itself, not the whole building or not the whole structure. So it is part of it or members of it. Also, the last one is the wind can have dynamic effects on the structure. As the wind is a dynamic force, so it can also cause dynamic effect on the structure, like something like that. So this can be moved in this direction and go back to its original position and go back to the other direction. So all of this is considered as dynamic effect on the structure. But in our course, we will not be considering internal pressures or drag forces or dynamic forces. Okay, do you have any question, guys, about how the wind actions affect the building? Any question, guys? Okay, now we can go to the next step. The next step is how to calculate the wind action or how to find the wind forces applied to the building. In Australia, we have two standards that are used in or to find the wind actions. The first one is 1170.2 version 2021 wind actions. This standard includes or will deal with the building and structure with height less than 200 meter and roof spans less than 100 meter. So if the buildings exceeding 200-meter height or like skyscrapers or any other long high buildings or roof spans more than 100 meter, like very long buildings like stadium, for example, these are not considered by 1170.2. So we need to find another standard to or special standard to find the wind on this building. So this means that this standard can be used for this building or this high-rise or medium-rise buildings here, and can be used for residential housing like that, but can't be used for stadium, for example. So it cannot used for stadium, but can used for this other three. And it can also, this standard can also work to find the wind on offshore structure or bridges or transmission towers, like this three type of buildings. But we will need to have more information to find this wind load on this type of building. So it is not straightforward for the offshore structure and the bridges and transmission tower. Need more research and need to have more information. Okay, so this standard is the main one used for wind calculation in Australia, but we will not be using it in our course. So this one, just for your information, but not to be used in our calculation. Because in our calculation, we will have a simplified version, and this version also has a name, the standard AS4055 2022 wind loads for housing. So there is a light version of the wind load calculation for construction managers, so that you can have some idea about how to calculate the wind load and how the wind load calculated for housing for houses. But there is some conditions to use or limitation to use this type of standard. So the standards to be used, we need to have the first step, which is check the limitation. The limitations are the building widths need to be maximum 16 meters. So if it exceeds 16 meter, you need to go back to use 1170.2. And the height, the maximum height is 8.5. The building need to be only 1 or 2 story maximum. So if it is more than 2 story, you can't use this standard. The maximum roof pitch is 35. The maximum eave height 6 meter. Okay, so these are some requirement or some limitation for using this standard. If it is on a slope, so the maximum step slope is 3 meter. Again, 1 or 2 story. maximum height 8.5, maximum width 16 meter. So the maximum width for all cases 16 meter, and the maximum height is 8.5 meter, and the maximum eave height is 6 meter, maximum roof pitch is 35 meter. So this standard is the standard we will be using in our course, so that the limitation of this standard will be satisfied in our course. But this limitation is in general limitation for you if you try to use or to try to find the wind loads. So you need to check these limits before using the procedure and formulas in this standard. So this our step number 0. And this was for the elevation. For the plans, again, the maximum width of the building is 16 meter. So anywhere the maximum width is 16 meter. And L less than or equal to 5W. L is the length of the building. So for example, if this 10 meter, so this should be less than 50 meter. So L should be less than 50 meter. This what is this instruction mean? L should be less than or equal to 5W. So based on W, the maximum L can be determined. If L exceeds this, you need to use a different standard, which is 1170.2, for example. Okay, so this are the first step or step number 0 before getting into the standard to find the wind loads. And then after we decide to use 11 AS 1455, so we have some steps to find the wind loads. So we have firstly 4 initial steps to find the site wind classification in page 10 of the standard. So we have firstly to find 4 parameters, or we to calculate 4 parameters before starting our wind procedure. The first step is to determine the wind region. How to determine the wind region? So this is step number 1. I will explain step by step. So the wind region means where the building located within the Australian map, because the Australian map, the standard has divided the Australia or the Australian map to 5 wind regions. As you can see, this light green is region A, and this light blue is region B1, and this dark blue, this light yellow region B1. This dark yellow is B2 on the coast here, the second area near to the coast. And the area near to the coast from the north is region C. And finally, this area to the west here at Port Hedland in Western Australia is region D. So we have region A, region B1, region B2, region C, region D, 5 regions. Region A is the least extensive one, and then it go more extensive wind when you move from B1 to B2 to C to D. So the most severe is region D. Region A and B1 are considered as non-cyclonic wind regions, so no cyclonic or cyclones are expected in those areas. But B2, C, and D are considered as cyclonic wind regions. So we have cyclonic and non-cyclonic wind regions. A and B1 are non-cyclonic, B2 and C and D are cyclonic. Okay, so these are the regions. So the first step is you need to decide or to determine what is the wind regions for your building. For example, if you are designing a building here in Adelaide, so Adelaide is region A, so it is non-cyclonic region. For example, if you are designing a building in Port Hedland, so Port Hedland is a cyclonic region, so it is D region. Okay, so this is a simplified map. The map from the standard is here. So this is, if you go to the standard from this link, you will find this map. So same criteria, same division of the map and same regions, A, B1, B2, C, and D, but with more cities. So for example, if you are Melbourne or Sydney or Adelaide, all these are region A. If you are, for example, in this region, Karumba, for example, it is region C. So this has more cities explained or shown on this map. But anyway, you can use this or this map in your design or in your project. So this was our first step to determine the wind region using the Australian map and based on the location of your building. The second step is to determine the terrain category or terrain category. What does the terrain category means? If we go to this slide here, the terrain category means the obstruction effect on wind loading. So when the wind blow, the surface or the ground surface and the obstruction on the ground surface affect the speed of the wind or the intensity of the wind. So that we need to consider the terrain effect on the wind load calculation or the wind pressure calculation. Okay, so the standard has give us 4 classification for terrain category from TC1, TC2, TC2 2.5 and TC3. TC1 is for very exposed open terrain with few or no obstruction and or water surface. So this is very open area. TC1 is open area without any obstruction or very, very few, like 1 or 2 maximum. And open water surfaces like desert and so on. Oceans, near ocean and so on. TC2 or terrain category number 2 for open terrain, including grassland with self-scattered obstruction, no more than 2 per hectare. So let's say TC1, 0 or 1 obstruction. TC2 is 2 obstruction. So if you have grassland with 2 obstruction per hectare, hectare is equal to 10,000 meters squared here. So if you have only 2 obstructions per hectare, this means TC2. TC2.5 is more obstruction than TC2, which is terrain with few trees and obstruction fewer than 10 building per hectare. So if you have 2 to 10 obstructions per hectare, this is considered as T.5, 2.5. TC3 is a terrain with numerous closely spaced obstruction, like in suburban housing or industrial estates. So TC3 is a terrain with most obstruction, more than 10, like in cities, suburban cities, or light industrial areas. TC 2.5, between 2 and 10 obstruction. TC2, 2 obstruction. TC1, 0 or 1 obstruction. This can be interpreted to this diagram, which show you the difference between TC2 and TC1 and TC3. As you can see, TC1 here, like you have water surfaces, desert land, very open area. We have only one building and almost no obstruction around this building. So this is considered as TC1. TC2 here. So is this your building, for example? You are designing this building and you have only 2 or less obstruction around. Like this one and this one. TC.5, so you have building and a little bit very closed space, like you have 2 and up to 10 obstruction. So this is considered as TC 2.5. TC3, as you can see here, TC3, you have very closely spaced building around your building. So this is like normal cities or cities and light industry areas. So this is number 2, step number 2, which is finding the terrain category based on how many obstruction around your building. Step number 3 is determine the topographic class. The topographic class means how is the surface or the topography around the building we are designing looks like. So this means if we have hills or mountain around our building. So let's look about this parameter here. So how to determine the topographic class of your building. So the topographic class is using this table here is the topographic class measuring the effect of wind on a house on a rising ground. Rising ground like hills or escarpment or mountains or ridges and so on. So this can be given by table 2.4, as you can see. This depends on the slope of this hill or the slope of this area, and we have like divide the slope or the hill to 3 parts: zone, lower third zone, mid third zone, and top third zone. If you look to this diagram here, so this diagram explain what is meant by this parameter. So for example here, this is our design building. So this building, as you can see, was constructed over a hill. So the wind is affected by this change in the topography, so that we need to include or consider this in our calculation. So for example, if the hill height is h here, as you can see, or here, so the standard has subdivided this h to 3 parts or 3 thirds. Those 3 thirds are top third, the top third of the height, mid third of the height, and lower third of the height. So you have top third, top third, mid third, and lower third. So these 3 thirds are the thirds given by the standard. This will help us to find this parameter. And phi is the slope of the steepest measured slope in the top half of the cross section of the site. So this is the slope of this hill. Okay, so this is some explanation or some data needed to find the topographic class. This topographic class is ranging between T0 from T0 to T5. So based on the slope of the building, based on the location, if the building in your lower zone or mid zone or third zone, it can be T0 or T1 or T2 or T3 or T4 or T5. In the project, it is given to you directly if the building is T3 or T2 or T4. So based on your group, you will find this information. But if you need to find yourself, so you need to know the location of your building in regards of the hill, and find the slope of the hill, height of the hill, so that you can enter this table using this data to find your topographic class. Okay, so this was the third parameter, or the third third parameter we need to find before starting our wind calculation. The last one is determining the shielding class. So the shielding class means how the building surrounding the designed building affect the wind. So if we go to the shielding class here, so the shielding class, when the wind speed on the house is affected by obstruction with similar or higher size of the house. So this means if you have a house near to your designed house, higher or same height, so this will reduce the wind forces applied to your building. So we need to consider the building surrounding the design building in our calculation. One hint from the standard is groups of trees with similar faces to the house are considered shielding element in region A and B1 only. So in non-cyclonic areas or in non-cyclonic regions, the trees can be considered as shielding, but in other regions, only buildings or only houses higher or same high than our building can be considered as shielders. The standard give us three types or three classification of shielding for our design. The first one is full shielding, second one is partial shielding, and third one is no shielding. So full shielding means the building surrounding the design building is making or preventing most of the wind from this building, and that's why it's considered as full shielding. So full shielding, typical suburban areas with 10 houses per hectare. So for suburban areas with more than 10 houses can be considered as full shielding. So if you are designing a building in a city and surrounding by many houses, like 10 or more houses per hectare, this is considered as full shielding. Partial shielding in areas with at least 2.5 houses or sheds per hectare. So if you have areas with less number of houses, like uh, far suburbs or not suburban housing area, so it can be considered as partial shielding. No shielding means that in this area you don't have or have less than 2.5 houses per hectare. Example for that is open parklands or open areas with less or very few houses. Also in the also in the project details, you will find that the shielding condition is given to you if it is full shielding or partial shielding or no shielding. But if you want to find it yourself, you will need to go to the standard based on the number of houses or the location of the building to find if it is full or partial shielding or no shielding. Okay? So now, after we found these 4 steps, after we finalize these 4 steps, so now we can find how much is the side or what is the side wind classification from page 10 of the standard. So these 4 steps are required to only find the side wind classification. So how to do how to determine the side wind classification? you need to first determine the wind region, number one, determine the terrain category, number two, determine the topographic class, number three, determine the shielding class is number four. So these four steps are just to find the site wind classification. So if we go to this table here, this table is the site wind classification based on the parameter we have found earlier. So for example here, to enter this table, we need the first step is the wind region. So you need to find the wind region. Number two, you need to find the terrain category region. Number three, you need to find the terrain, or sorry, topographic classification. Number four, and the last, as you can see here, you need to find the shielding parameter or the shielding class. So you need to find wind region, number one, terrain category, number two, topographic classification, number three, and shielding classification, number four. An example of that is if we have a building in wind region A, so this number one, and the terrain category for this building is 3, so TC3, this number 2. And the topographic class for this building is T1, so this is number 3. So if you can see here, this triangle here, or this parameters here, this is for T1 topographic class. Under topographic class, we have FS means full shielding, BS means partial shielding, NS no shielding. So again, A, TC3, T1. So under T1, you will need to select if it is TFS or BS or NS. So in our case, it is full shielding. So what is the final what is the final class? The final class is N1. So for example here, for topographic, for wind region A, for wind region A, and TC3 and T1 and full shielding FS. What is the final classification? N1 is the wind classification. Okay, so all this give us wind class N. So now if we go back to our steps, the first step is to find the wind classification based on wind region, terrain category, topographic class, and shielding class. Okay, any question about the first step? Do you have any question, guys? No question? Are you still there? No question, guys? Thank you, Jörg. Thank you, Ismat. Okay, guys, so for the first step, we have found the site wind classification, and now we may take a rest or a break for 8 minutes, and then we can continue. So we will continue at 2:10. Okay, so we have a rest for just 10 minutes and see you later. See you in 10 minutes. Thank you. Okay, guys, can we start again? So just summarizing what we have done already in the wind calculation using using AS 4055. That the first step, we need to determine the wind region, terrain category, topographic class, shielding class. Those 4 steps will be used to find the site wind classifications from table in page 10 of the standard. Here. So for example, if we have region A and TC3, T1, and full shielding class, so we will use table 2.2, the site wind classification, to find the site classification from N1 to N6. Our focus will be only on these 2 classifications, A and B1, not the whole. So if you look at your project, you will find the wind region is A or B1. So using region A, TC3, so this line here, and in TC3 we need to find if it is what is the topographic class. So the topographic class is T1, so one of these 3. Then the full shielding class, so we have FS or BS or NS, so we will use FS. So the final answer or the wind classification will be N1. So N1 will be our classification for the wind. Okay. So this is what you need to do in your project as well. So the region will be given to you, and the terrain category and the topographic class and shielding class. So what you need to do is just to go to this table to find how much is the classification N1 to N6 based on your group. So now if we go back to our steps or our procedures. So the first step was to find the site wind classification. The next step will be how to find the design gusset wind speed. So the next step is find the design gusset wind speed. The design gusset wind speed will be based on the site wind classification. So after you find site wind classification, you need to go to table in page 6 of the standard to find how much is the gusset wind speed. So if we jump to this part in the slide here, so if we look to this part, so this is the tables for the gusset wind speed. So the gusset wind speed is based on the site wind classification, if it is A or B1 or B2 or C or D. So for example, in our example we have N1 wind classification. So how much is the design gusset wind speed? 2 values. We have 2 values. One value for surfaceability limit state, one value for the ultimate limit state. So in your calculation, you will need to find 2 values. These 2 values are 26 meter per second for surfaceability. Ultimate is 34 meter per second. So the design gusset wind speed are 2 values. The design gusset wind speeds are 2 values, one for serviceability and one for ultimate. Ultimate means we are designing the structure for failure. Surfaceability is used when we design for deflection or we checking the deflection. In your project, we will need the two values, so you need to find the two values, 26 and 34. So these two values are required in the assessment or in the project. Okay, so if we go back to our procedure again, I want to show you step by step. So after we find the site classification, we go to find the design gusset wind speed. Then the next step is to find the wind pressure coefficient. So after you find the design gusset wind speed, you will need to find the wind pressure coefficient, the next step. So if we go to the next slide. Here. This is a formula we will use, just delay this now. Okay. So this is a coefficient for pressure. So this is the wind pressure coefficient. We will need this wind coefficient to find the wind pressure. So after we found the gusset wind speed, we will need to go to table 3.2.1, 3.2.1, the pressure coefficient for roof and wall for wind classification N1 to N6. This for regions A and B1 for ultimate and surfaceability limit states. So we have one table for non-cyclonic regions, and we have table for cyclonic regions. And as we have mostly working with non-cyclonic because the project is in Adelaide and the shed in Adelaide, so you will be working only or mainly with this part here or with this table here for non-cyclonic. So as you can see, we have three types of parameter we are looking for. We have general roof for general areas and roof edges and walls. This because the wind pressure is changed over the roof based on the location of the roof. So if you look to this sketch here or this diagram here, so this is the pressure zones on the walls and roof. So as you can see, the roof by the standard is divided to G areas. G areas is the white areas or general areas here. So these are general areas like this one, this one, this one, this one. So these areas are not near the edges of the roof. And then we have roof edge areas or RE areas like this one here, this one here, this one here, and this one here. So all of these areas are roof edge areas. So the intensity of wind is more on the roof edge area. So G or the general area is the least one. Roof edge areas is more values, and the highest value of wind are at the corners. So row RC or roof corner or roof edge corner like this one here. So roof corner, which is at the corners of this building. So here as well, roof corner, and here as well, roof corner. So the roof in the standard is divided or subdivided to three main location: general areas, roof edge areas, and roof edge corners. If you remember our last week tutorial, we mentioned that the Berlin spacing is smaller near to the edge. That's why it is smaller near to the edge, because if you see here, this part of the roof very close to the edge, and here as well, and here as well. So all these areas, the wind is higher. The wind load is higher or more intense. That's why we need the purlin to be closer to resist this loads. Okay, so this is how the standard divides the roof. And if we go back to the table, so this table, we have the different areas of roof. For the walls, no, there is no problem with the wall. The wall is not subdivided the same. But what we will be looking at, so we are looking only on the general areas. So in your project and in our calculation, we will be only focusing on general areas of the roof and general areas of the wall. So no looking at this one or this one or this one or this one or this one. So in your calculation, our focus, it is written in the details. We need only to calculate the wind on the general areas of the roof and general areas of the walls. Now, if we look to the reminder of the video, the parameter itself, as you can see, this part of the table here, we have three type of parameter. We have external pressure, internal pressure coefficient, and net pressure coefficient. So for your calculation, if you are designing this outside, like for real structure, you need to check these three factors. But in our project, for simplification, we will be only working on the net pressure. So no external pressure, no internal pressure, sorry, no external, no internal, and only our focus will be only on the net pressure. So we will be designing or calculating the wind load only for the net pressure. So for example, if we are calculating the coefficient for roof general areas, you will be considering only these two factors for net pressure, negative 0.1 and positive 6.63. If you are designing the wall, so similarly, you will have two factors for net pressure coefficient, positive 0.9 and negative 0.77. So the factors are four factors we'll be using, two for roofs, negative 0.1, positive 0.63, and for walls, positive 0.9 and negative 0.77. What is the positive sign means and what is the negative sign means? The positive sign indicates we have pressure or towards the surface. So if the coefficient positive, this means this force is pressure. If the sign of the parameter is negative, this means away from the surface or suction. This means that negative 0.1 is suction, positive 0.63 is pressure. For walls, we have positive 0.9 pressure, negative 0.77 suction. What does the two values mean? The two values mean that we have two cases of wind loads applied. One suction and one pressure for walls, and one suction, one pressure for roof. So you need to consider both of them in your calculation. So this will make us have more than one value for roof and more than one value for floor. Okay. Do you have any question with the parameters or the coefficient, guys? Any question about the coefficient. So if you are again, to summarize, if you are calculating the roof pressure general areas, so you will go to the net pressure column and find the parameter as -1, positive 0.63. For walls, only general areas as well. So we have net pressure as well. So we have positive 0.9 and negative 0.77. Positive means the pressure, negative means suction. Okay. So now if we go back to our procedure, after we found the wind pressure coefficient, we go to the next step, which is the wind pressure. How to use these parameters, the coefficient, the pressure coefficient, and gusset wind speed to find the wind pressure. This formula can be found in page 2022 of the standard, and we can find it here in this slide. Calculation of pressure or suction. The formula to find the pressure or suction is B equal to QU times CB. So this is the formula we will be using after we find the speed. And so to use this formula, you will need two things. Number one is the design wind speed, and is number one. Number two is the pressure or wind pressure coefficient. So if you have these two parameters, this number one, number two, you will be able to find the pressure. So the pressure equal to QU times CB, where B is the design wind pressure normal to the surface in kPa. This is what we want. And QU is the free stream dynamic gusset pressure. So this is the gusset pressure. And this gusset pressure is calculated using this formula here. QU equal to 0.5 rho air times VH squared divided by 1,000. Okay, so we have QU again equal to QU is the free stream dynamic gusset pressure, and we use it in this formula here. So this is our QU needed to find the pressure. The formula for this QU is 0.5 rho air times VH squared divided by 1,000, where rho air is the air density equal to 1.2 kilogram per cubic meter. We will understand this better in the example, in the tutorial, but this is just to know how to find the wind. So rho air is a constant value, 1.2 kilogram or kg per cubic meter. So rho air will be known for us. 1,000 is a constant. So what is VH? VH is the design wind speed. So we already find the design wind speed in the previous step. So design wind speed will be used to find QU. Okay, so QU 0.5 rho air times VH squared divided by 1,000. This value will be in kPa. So the unit for this value will be kPa. Okay. So the unit in kPa. What is kPa equivalent to? If you remember, kPa is equivalent to kilonewton per squared meter. Right? So kilonewton per squared meter is equivalent to kPa. This is similar to the units we used for dead load and live load calculation. Then what is CB? CB, as you can see here, is the pressure coefficient, external or internal or net as appropriate. So as I mentioned earlier today, or as I mentioned earlier, we are not working with external and we are not working with internal. So in your project and in this course, you will be only focusing on net pressure. So CB in this formula here are the pressure coefficient we found earlier. So CB known for us, V design wind speed known for us, so you can find CB and QU, then you can find the pressure. Okay. Any question about that? So this is how to find the pressure. So what you will do, just find the design wind speed as we mentioned, find the pressures as we mentioned, multiply the speed in this or substitute the speed in this formula to find QU, then multiply QU times CB to find B. Okay, so this is the pressure calculation. Now, if we go back to the step, our last step is to convert this pressure to the wind loads. So the pressures are force per unit area or force distributed over area. We need to convert this pressure to wind loads on our beams and columns or our members. So the last step is to convert the pressures to wind loads. So after we found all this coefficient, now how to convert the pressure to load per unit length, transfer the load to the column or beam. Do you know how to do that? So I will just add a slide here quickly. So now if you have a wall like this is a wall. So what we have done already is we found some pressure distributed over this wall here. Okay, so again, these pressures are B equal to QU multiplied by CB. So this is the wind pressure. Okay, so after we found this wind pressure already from the previous step, we need to convert this to a column. So if we have one column here in a different color, we have a column, this column here in black. So what we need to do is convert this pressure to this column. This pressure will be distributed load over the column itself, a length of the column. This is like what we have done in the dead load and live load. You need to convert from a line area load to line load. So how can we do that? We need to first find the tributary area for this column. The tributary area for this column, for example, will be something like that. So this area between the two lines, I will not be able to color it, but anyway, this area here with this width. So this width is called the load width, if you remember. So this column will carry the load width. So wind load will be equal to the wind pressure times the load width of this column. So this is very simple. So the wind, after you find the wind pressure, you find the wind pressure using this formula. Okay. Then you find the wind load using this formula. So wind pressure equal to wind load equal to wind pressure times load width. Similar to this example here. So this is wall, this is the wall, and this is the column. So our final job is to find the distributed load over the column and over the beam. So the first step, you will find the pressure, then multiply the pressure by the load width to find the load as uniform load. Okay, so if we look at this example here, as you can see, so for example, if this beam or column, so the beam, for example, is carrying the wind from the, can you mention? From the roof. So the beam, if this beam, so the beam carrying the wind from the roof and the column carrying the wind from the wall. Okay, so if you want to convert the pressure on the roof to a beam, so you need to multiply the pressure times the load width of the beam. So if this the tributary area of the beam, and we have the load width or the wall width is our, let's call it load width instead of, so it's called load width, and we have the load width. So the uniformly distributed load or wind load, as I mentioned, will be equal to pressure, the wind pressure times the load width. So our last step to find the wind loads is to multiply the pressure times the load width. Okay. Do you understand the wind calculation, the procedure? Do you have any question, guys? Any question? So if we want to summarize what the steps again last time before we go. So the steps are mentioned here in this slide. So we are using the standard 40-55 to find the wind loads on the buildings. The first step is to determine the wind regions and then determine the terrain category, determine the topographic class, and determining the shielding class. All this step just to find the site wind classifications in page 10. Using the site wind classification, you will go to the table 2.2 to find the gusset wind speed. Using the gusset wind speed, you can find also the wind pressure coefficient. After the wind pressure coefficient and with the gusted wind speed, you can find the wind pressure using the formula B equal to QU times CB. And finally, after you find the pressure, multiply the pressure by the load width to find the wind loads. So this slide has a summary or a flow chart of how to find the wind loads on the beam and column, and the steps are explained in the slides here, so you can have a look on them, and we will solve an example on this in tomorrow class, Wednesday. So if you have any question, we can do it, answer it now or tomorrow. And thank you. Do you have any question, guys? Do you have any problem with the assignment or the group? Thank you, Syok. Okay, guys, thank you for attending today, and we'll see you in the class tomorrow. Enjoy the rest of your day and see you next week.